Good morning all and welcome to our gas distribution systems presentation. My name is Collett. I am the Fabrication and Assembly Services Manager here at Swagelok, Sub-Saharan Africa. I'll be taking you through today's slide deck.
So a brief overview of today's topics, starting with our gas distribution overview. We will then take a look at pressure regulation selection criteria, followed by some information regarding the Swagelok gas distribution systems. So as we all know, any gases and gas distribution plays a critical function in all our industries. Without effective supply and control systems, many plants may not be operating as effectively as possible. Gas distribution systems are often built around one or more of these systems, from supply to control or regulation down to the point of use. If we take a look at some of the design and locations, so looking at the systems on your screen, the layout on the left is a typical lab installation, the layout on the right, maybe a container or some form of analyzer shelter. So we start with the supply system that is found at the start of the gas distribution system. These systems are typically responsible for the storage and the supply of the gases needed downstream. Following the supply system is either going to be some form of control or changeover panel. These panels are typically responsible for reducing the pressure from the supply system to a more manageable and suitable pressure downstream for the application. Let's go back a step. So then going from our supply system, we are then going to either have a control panel or some form of changeover panel. These panels are typically responsible for reducing the pressure from the supply system to a more manageable and suitable pressure for the application. And then finally, feeding into our lab or near the final application, we would have some point of use that's typically responsible for the final pressure control and monitoring. All of these systems, though, do require some form of pressure control or regulation. When selecting a regulator, there's a variety of selection criteria that you need to take into consideration, starting off with the function of the regulator. For the most part in these gas distribution systems, you would typically want a regulator to reduce the pressure. So now that you know your function, what you would be looking at is the inlet pressure currently feeding from your bottles to the outlet pressures or the control ranges you would like downstream, focusing in on the tolerable ranges that you would need. Not all systems have one set pressure. You might need to select a pressure regulator that has a range. From there, you would look at your media. Your media then would be determining what type of materials of construction your regulator is made of, either your elastomers or your alloys, and then take into consideration your temperature, as this can affect some of those alloys or elastomers that you have previously selected. When looking at regulators, you typically think you'd want to select a regulator for pressure control, but you do need to take in flow rates. You need to take in flow rates into account, as some regulators tend to lock up should the flow exceed what is allowed through the regulator. And then finally, you would consider your end connections and other features that your regulator might need, such as a captured vent. This may seem like a lot of information to take through, but Swagelok has coined the stamped terminology, which is the easy way of remembering what you need to work through when selecting a regulator, such as size, temperature, the application, the media, the pressure, the type of end connections, and what kind of delivery that you would need downstream. One important fact to consider is there is no such thing as a one-size-fits-all regulator. Not all applications are the same. Each application is unique. All right, so let's take a look at factors that may affect regulator performance. We're going to be taking a look at 4 different factors in these next couple of slides. Starting off with seat load drop and or lockup. So seat load drop occurs when you open a valve downstream of the regulator to allow flow. If you take a look at the graph on the top left-hand side, over here we've got the 2 arrows pointing to seat load drop. You can see you're going from a 0 flowing position, and as we open this regulator set flow or open a valve downstream, you are going to notice a drop in the outlet pressure of the regulator. Conversely, if you close this valve downstream, the result is lockup, where you go from a flowing position to a 0 flowing position in your system. And to demonstrate this, I have a video on the next slide. So as you can see, the regulator was set at 1 bar in the static position, and as the valve was actuated downstream, although the regulator was set at 1 bar, the pressure did drop down from 1 bar down to almost 0, and as the valve was actuated to the closed position, you saw lockup occur as the pressure spiked back up to 1 bar. So once we move further down the graph, we then get to what is known as droop. So let's say, for instance, if we set our regulator at 4 bar, the maximum amount of flow that you are going to get through your system is roughly 2,400 liters per minute. So as the flow increases downstream, and this could be for many reasons, it could be an increase in demand, you could have potential leaks downstream. You will notice that as the increase in pressure, as you get an increase in flow, the regulator then drops in the outlet pressure that is able to supply. So as we get to about 3,000 liters per minute, you then end up being able to output a maximum of 3.5 bar. Anything past that, and it results in choked flow. So choked flow is when the flow exceeds what the regulator orifice is able to provide, which is this section down here. So if we get an increase in flow, anything past, let's say 3,900 liters per minute, you can see a substantial drop. So at this point, the regulator is wide open, just with a whole lot of flow downstream and not being able to regulate any pressure. What you want to be focusing on is, when selecting a regulator, is focusing on this ideal operating range. The last one we would take a look at is supply pressure effect, or SPE. So SPE, supply pressure effect, is a ratio describing the change in outlet pressure per 1,000 psi change in the inlet pressure. So typically the Swagelok KPR series has an SPE of 1%. So if we watch the graph here, as the upstream pressure of the cylinder is depleted, the downstream pressure is increased by 1%. So what you'll notice is we've started at 3,600 psi, we've moved down there, so we've used 1,000 psi worth of gas, so this results in 1,000 psi difference. 1% of 1,000 psi is 10 psi, so you will notice an increase in 10 psi on the outstream side of the regulator. So this particular video, the system is feeding from right to left, and you'll notice that as we decrease the pressure on the right hand side, you would have noticed an increase in pressure on the left-hand gauge. I'll play that once more for you. Right, I'm just going to play you a quick video describing supply pressure effect. This is a video that was made by our factory in the USA.
Welcome to this Swagelok video. Today's topic is considerations in managing the supply pressure effect of a regulator. For lower flow applications, an alternative method of regulating supply pressure effect is to use two-stage pressure reduction. This can be accomplished by using two single-stage regulators installed in series, or the two regulators may be combined into one assembly. To calculate the variability of outlet pressure for a two-stage regulator setup, the inlet pressure difference is multiplied by the SPE of each regulator, as illustrated in the following equation. The first stage regulator controls the inlet pressure variation to some degree, while the second stage regulator controls it further. Together, the two regulators bring the outlet pressure very close to the target. We will use a KCY model regulator and return to our supply pressure effect example. The cylinder empties from 172 bar to 34 bar, or 2500 psig to 500 psig. Assume that each regulator has a 1% SPE. With a 137 bar or 2000 psig inlet pressure drop, the first stage regulator will experience a 1.3 bar or 20 psig increase in outlet pressure. As a result of that increase, the second stage regulator will experience a 0.01 bar or 0.20 psig decrease in outlet pressure. The net result is a minimal pressure decrease that is only 0.01% of the initial cylinder pressure drop. 0.01 bar or 0.20 psig equals 137 bar or 2000 psig times 0.1 times 0.1. Once the cylinder pressure drops below the first stage setting, in this case 34 bar or 500 psig, or the SPE of this regulator is no longer applicable and only the SPE of the second stage regulator is taken into account. Then the assembly will behave like a single stage regulator. Notice how the effect on the outlet pressure is lessened from the previous regulator arrangements. Applications that require a gas cylinder supply multiple operations with at least one operation requiring a different pressure. You will need to use two-stage regulation. The first stage regulator will be located near the gas source and a second stage regulator located on each of the process lines. Be sure to avoid the costly mistake of using a two-stage regulator at the gas supply source and a single-stage regulator at the point of use. This setup is equivalent of three-stage regulation. With a regulator controlling outlet pressure from a gas cylinder, supply pressure effect is a phenomenon that will always be present. Whenever there is a change in inlet pressure, there will be a corresponding change in outlet pressure. You can minimize the effects of supply pressure effect for many applications by using a single regulator with a balanced poppet design or by using a two-stage regulator. But if your gas source is servicing multiple operations with different pressure requirements, you may need multiple single-stage regulators, one near the gas source and another on each process line, to in effect provide two-stage regulation at each point of use. Refer to Swagelok.com in the product literature for additional information. Thank you for watching. We will continue to develop videos like this to help you get the job done. Get more information by watching our other videos or contacting your authorized sales and service center.
Great. Well, hopefully that video has explained supply pressure effect slightly better than I could. So finally, I would just like to touch on the gas distribution systems we are able to supply here at Swagelok Sub-Saharan Africa, starting with the Swagelok source inlet. As mentioned before, this is the start of the system where your supply and storage take place. These systems are available in a variety of configurations depending on your needs. These systems, however, do have a maximum pressure rating of 300 bar, but I think our standard bottles are typically between 2 and 250 bar. Next, we'll take a look at our Swagelok gas panel. Typically following right after the supply or source inlet, these systems are your first point of pressure reduction of the system. From there, they're typically feeding lines off into the larger distribution network. These systems are either available with the single or dual stage pressure regulation, depending on your system and the needs of the plant. So you could start off with a single stage regulator here, and closer to the application, you could include a second pressure regulator. These systems are super easy to configure and have a variety of configurations, such as including captured vents or even some form of overpressure protection. Depending on your system media and the requirements, these systems are available in stainless steel and brass. Next, we'll take a look at one of my favorite systems, the Swagelok changeover system. This is a truly automatic changeover system with no human intervention required to change over from one cylinder bank to the other once one of the supplies has been depleted. Like the Swagelok gas panel, these systems are found right after your pressure supply. These systems as well can be configured with captured vents to safety vent off any excess pressure when changing out your cylinder supply. These changeover panels are found in applications where large amounts of gas is being used, or in critical applications where you can't afford the application to run out of gas mid-run. So let's take a look at a manual system versus an automatic changeover. If we notice the sample cylinder on the left-hand side, you can see this is on a manual system, and we're currently going through normal service. You start using the gas in the bottle, and it eventually depletes to the empty state. At this point, if you don't have any alarms or some form of signal in place, you're not going to know if your system has run out of gas unless something critical happens downstream or some form of failure happens. At this point, you would have to manually change over your system to your reserve cylinder, and it would deplete, right? So this can be quite time consuming. If it is in a remote location, you now need to get maintenance out there to go and change out your cylinders. If we take a look at the automatic changeover, this allows for uninterrupted gas or liquid supply. So you'll notice that it will start feeding from the left cylinder, and once this reaches the empty stage, it will automatically change over and start feeding from the right-hand bottle or your reserve bottle. So these systems are... So you can also upgrade these systems to include configurable alarms. So once the cylinder on the left-hand side has run out, this will send a signal to your control room informing you that the system has been depleted on gas and that you do need to send a team to change over the primary feed bottle. This can be all done online while feeding from your second bottle. So how does the operation look on these? So this is a typical layout of a Swagelok changeover panel. There is the PNID in the bottom right-hand corner, but essentially we have two regulators connected with a common outlet. These are tied together with the handle in the middle. And then from there we have an optional inline regulator. This can count as your second stage of reduction. But again, it is optional. You can reduce at your point of use downstream. So how this works is we have a primary regulator. Let's say, for instance, it's the regulator on the left-hand side. This is set at typically a higher pressure than the one on the right-hand side. So let's say, for instance, the regulator on the right is set at 12 bar, and the regulator on the right-hand side is set at 10 bar. They're tied by a common handle, and the handle indicates what is the side that is being consumed from. So at this point, regardless of which way your handle is pointing, the regulator with the highest set pressure will be delivering the gas. And the regulator on the right-hand side will not flow until the outlet pressure of the regulator on the left-hand side depletes below that point. So we mentioned that the regulator on the left-hand side is set at 12 bar. The regulator on the right-hand side is set at 10 bar. So once your supply depletes on the left-hand side, the system will, once it depletes past 10 bar, the system will automatically start feeding from the right-hand side, thus it being the greater pressure than the one on the left-hand side, and will feed through downstream. Okay, so in order to feed from the right, we can pick whether we wanted to feed from the left or the right. I mentioned earlier that tied handle, so we could essentially just pull that handle down, pointing the arrow to the right-hand side, and what this does, it would increase the pressure of the regulator on the right-hand side, essentially taking it up to 12 bar and reducing the pressure on the regulator on the right-hand side down to 10 bar. These systems come equipped with a check valve at the bottom here, which stops any fluid flow going back through the regulator to your cylinder bank. This feature also enables you to change your cylinders while the system is currently online. And then finally, we have our point of view system. As mentioned, this is the last point of control prior to the gas being used. These are small and compact systems that can be mounted to your walls and your test benches, depending on where they're being used. They offer a modular design, so products can be changed as needed depending on your application. So here at Swagelok, we have developed an internal configurator. Once we've required the information of the application, with just a few clicks, we can generate a complete design with a bill of material. Should there be any special requirements, as mentioned, these systems are highly configurable and can be customized to suit all of your needs. And then finally, once we have settled on a design for your application, these systems are built locally right here in our fabrication and assembly workshop.